The fundamental theorem of algebra says that basically all polynomials have at least one complex zero, or one complex root. Now we say complex only because it means that I can write any zero in the form a plus bi. But just because it's written in complex form does not mean that it is imaginary. Those are two completely different things. So if I tell you that the root of a polynomial is 7, I can write it as a complex root by putting plus 0i. Now you know that 0 times anything is 0, so this just basically goes away. That's why you have this real number. And then we have something called the complex or complete factorization theorem. It basically says that all polynomials can be written as a times the sum or the product of x minus the first root times x minus the second root all the way down to x minus the nth root. So however many zeros or roots we have, we can write it completely factorized in this format. That includes whether the roots are 0 or imaginary. Let p of x equal x cubed minus 3x squared plus x minus 3. And I want to start this problem off by finding all the zeros. I'm going to talk about two different ways of going about finding the zeros of this particular polynomial. The first way is the way that I described in class, which is you graph it, and then you see that the graph hits the x-axis at 3. It only has one real root. That means the other two roots must be imaginary. So what we do is we use synthetic division to divide out that root. I'm going to be left with a quadratic equation that I will use the quadratic formula to solve. Now, when you factor out a 0, your remainder at the end will always be 0. If it's not, then your math went wrong somewhere. Alright, so we drop the 1, and then this is 3, then we add down, and then we multiply, oops, that should be 0, and then we add down, and then we multiply, and look, it adds up to 0. Remember, the quotient is always 1 power less than the original problem, so the quotient here is x squared plus 1. So if I have x squared plus 1 equals 0, I could use the quadratic formula, or this particular equation is easier to solve by subtracting 1, square rooting both sides, and then when I'm solving an equation where I end up with a negative under a radical or any other radical when I'm solving an equation, this is the case where we use the plus or minus sign in front, and the square root of negative 1 is I. So my three answers are 3, I, and negative I. The other way that I could have done this was I could have, I'm going to go back up here, I could have tried factor by grouping. Anytime you have 4 terms in a polynomial, factor by grouping is not a bad way of doing the problem. So you group the first 2 terms and the last 2 terms. So the first group shares a common factor of x squared, and I'm left with x minus 3. The second group, the only thing they share in common is a 1. Notice that both of these have an x minus 3 in them, and when I take the x minus 3 away, I'm left with x squared plus 1. So when I set this equal to 0, the zero product property says that one of the solutions is 3, and it says the other solution is, got to move this up, plus or minus I. So I could have done this in one of 2 ways. Now, does factor by grouping always work? No. I'd probably stick with using my calculator to find the real zeros, because if you have a higher order polynomial, then algebraic factoring techniques get a little cumbersome. In the next part, what I'd like to do is I'd like to find the complete factorization. So let's go back and write down our 3 answers. Factor, I should spell this right, is zation. So my three answers were 3, I, and negative I. So if I write this in factored format, I'm going to have A. The first factor is x minus 3. The next factor is x minus I. And the next one becomes x plus I because you're plugging in a negative I. A, if you know the leading coefficient of the polynomial, that's A. And in this particular case, A was 1. So this basically goes away. And this is the complete factorization. We'll talk about a problem later on where we're actually given information that we can use to find out what A is if we don't already know the original equation. Let's try this again. I want to use P of x equals x cubed minus 2x plus 4, and I'm going to start by finding all the zeros of P. So I'm going to start by graphing it, and I'm going to see that it only has one real solution. That one real solution is at negative 2. That means the other two solutions must be imaginary. So we're going to use synthetic division to divide out the negative 2. Remember, when you do synthetic division, you need to watch out for missing terms. I want you to notice that there's an x squared missing. So we need to put in a 0 in its place. Alright. 1, negative 2, 4, 2, negative 4, 0. Remember I said that if you find a real 0, its remainder better be 0. Now the remaining quotient is going to be 1 power less than the original problem. It's x squared minus 2x plus 2 equals 0. So now to find the imaginary solutions, we're going to use the quadratic formula. So x equals the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. I like to simplify this in parts. So x is equal to 2 plus or minus the square root of 4 minus 8 is negative 4 over 2. So this is 2 plus or minus 2i over 2, which simplifies to 1 plus or minus I. So my three solutions are negative 2, 1 plus I, 1 minus I. So now, when I want to go and find the complete factorization, I need to be a little bit careful when I plug in these complex numbers. All right, like I said, the leading coefficient was 1. So A is 1. So P of x is going to equal the first factor. Since the first 0 was negative 2, the first factor is x plus 2. But the next one's going to be x minus 1 plus I. Notice the double set of parentheses. The next one's going to be x minus 1 minus I. I don't like those double sets of parentheses, so I'm going to make this look a little bit nicer. The first factor that has a complex number in it is going to be x minus 1 minus I. And the next one's going to be x minus 1 plus I. And this would be the complete factorization of x cubed minus 2x plus 4. The zeros theorem tells us that the largest exponent of a polynomial tells you the complete amount of complex zeros, including all of its multiplicities. Remember that the multiplicities could be double roots, triple roots, and those get added into the total number of zeros. So in this example, I'm going to find the complete factorization of all 5 zeros of the polynomial 3x to the 5th plus 24x to the 3rd plus 48x. If you go and you graph this, you're going to find out that the only real 0 is at 0. So we're going to attack this problem in a little bit different way. I'm going to start by factoring it the old-fashioned way, which is, what's the greatest common factor? The greatest common factor that goes into all three terms is 3x. When I divide everything by 3x, I'm left with x to the 4th plus 8x squared plus 16x. No, 16 on the nose, sorry. Well, when we have a quartic polynomial that is a trinomial, we call that a quartic function in quadratic form. It factors like any other regular trinomial. If you pretend like it says x squared, you're going to find out that the two numbers that multiply to give you 16 but add to give you 8 are 4 and 4. So it's really x plus 4, x plus 4. But in this case, because of this, it's x squared plus 4, x squared plus 4. We write that as x squared plus 4 squared. So we have a complex zero that has a multiplicity. Okay, so now we're going to go back and we're going to talk about something that you do already know, which is remember the difference of two squares. This is really important. It just pops up so often. And it's not just the difference of two squares. It also has to do with what it factors into. A squared minus b squared always factors into a plus ba minus b. So if you ever have something in the form a plus ba minus b, you know what it multiplies to be. So if I gave you x plus 3, x minus 3, you would know that it would multiply to be x squared minus 9. Well, there's another problem that looks similar to this, I should say, and it's really the sum of two squares. Under the real number system, we can't factor the sum of two squares. However, under the complex number system, I can. Under the complex system, a squared plus b squared factors into complex conjugates. So if you have complex conjugates, you can go the other direction and know that it's going to multiply into a squared plus b squared. So I want you to notice this is a squared plus b squared. That means that this is going to factor into, nothing happens to the 3x, and the x squared plus 4, let's pretend like it looks like this. Sorry, my handwriting's getting a little sloppy here. Each of those x squared plus 4's factors into an x plus 2i, x minus 2i. But remember, there's two of them. So this really factors into 3x, x plus 2i squared, and x minus 2i squared. That is the complete factorization. When we do complete factorization, we want all the factors to be linear. That means that it has to have an x to the first. The polynomial up here was a quartic function in quadratic form. It factors like any other general trinomial. However, instead of having an x, when you're done factoring, you have an x squared. I now introduced you to a new special type of factor, which is the sum of two squares. It factors only under the complex numbers. So a squared plus b squared factors into a plus bi, a minus bi. Now let's go and find a polynomial equation if I know the zeros. I'm going to find a polynomial, p of x, of degree 4 with zeros I, negative I2, and negative 2. And I'm going to tell you that p of 3 equals 25. The p of 3 equaling 25, we'll come back to that in a little while. For right now, I want to focus on the fact that there were 4 zeros. And I want to write a fourth degree polynomial. So the first thing I'm going to do is I'm going to take those zeros and write them in factored form. In factored form, they are x minus I, x plus I, x minus 2, and x plus 2. The reason that that's important is because this is your complex conjugates being multiplied together. When you multiply them, if you want to FOIL, you can, but I would skip that. It's going to factor into a squared plus b squared. These are also conjugates of a sort. They're the product of a sum and difference. And when you multiply them together, you're going to get a squared minus b squared. And the reason it's really nice is because it kind of helps skip some steps. Now, you can multiply these together by FOILing. You get your x to the fourth minus 4x plus x squared, oops, that was an x squared, x squared minus 4, which we know is x to the fourth minus 3x squared minus 4. The problem is that what we haven't accounted for is the fact that there's an a. And since we don't know the original polynomial, we don't know what a is. But they gave us some information for finding it. They did tell me that p of 3 was 25. That means that y is 25 when x is 3. So I'm going to plug in 3 everywhere I see an x, and then I'm going to simplify this problem. I want to find out that 3 to the fourth minus 3 times 3 squared minus 4 is 50. And then I'm going to divide by 50, and I find out that a is a half. So p of x must be 1/2 times x to the fourth minus 3x squared minus 4, or you can write that as 1/2 x to the fourth minus 3/2 x squared minus 2. I claim to you that if you graph that polynomial, you will actually see it hit the x-axis at both 2 and -2. Now let's write a polynomial q of x of degree 4 with zeros -2 and 0, where -2 is a multiplicity of 3. Well, that's pretty easy. Your factors are going to be x plus 2, and the other one is going to be x. But they told me that this factor has a multiplicity of 3. Now, since they did not give me another ordered pair that lies on the graph, like in the previous example, I am unable to find a, so we just assume a is 1. In order to multiply this out, I want you to look at this, x plus 2 to the third power. I wonder if I can go back and review my Pascal's triangle to determine what that's going to be multiplied out. Remember, Pascal's triangle looks like this. So raising something to the third power means use the coefficients from the third row. So it's going to be 1x to the third plus 3x squared times 2 plus 3x 2 squared plus 1 times 2 to the third, which is x cubed plus 6x squared plus 12x plus 8. Remember, there's another x in front. And all I have to do is multiply everything by that extra x. And this would be the polynomial. I should call it q of x because that's what they called it in the original problem, whose zeros are at -2 and 0, where -2 has a multiplicity of 3. Let's find all 4 zeros of the polynomial 3x to the fourth minus 2x cubed minus x squared minus 12x minus 4. The first thing that I'm going to do is I'm going to graph it in the calculator so I can find any real zeros that exist. When I graph it, I find one of the real zeros is at 2, and the other one is between 0 and -1. Using the 0 function on my calculator, with -1 as my left bound and 0 as my right, I'm going to find out that the 0 is at -0.33333, which is -1/3. Those are my real zeros. That means the other 2 zeros must be imaginary. In order to find the other 2 zeros, I'm going to have to use synthetic division to divide these out. And then I'll be left with a quadratic equation that I can use the quadratic formula on. So I put 2 in my box. None of the coefficients are missing. So they are 3, -2, -1, -12, and -4. 3, 6, 4, 8, 7, 14, 2, 4, 0. Perfect. I wanted 0 as my remainder. Now I'm going to do this again, except now I'm going to put -1/3 in the box. Oops, I should make that line shorter. There. Alright, 3, -1, 3, -1, 6, -2, 0. So even though I had a fraction, it didn't turn out bad mathematically. Remember that every time you divide, you go down 1 power. The original problem was x to the fourth, which means this was x to the third, which means this is x squared plus 3x plus 6 equals 0. I'm going to need to use the quadratic formula on that particular equation. So, x equals the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. So x is negative 3 plus or minus the square root of negative 63 over 6. The square root of negative 63 is going to simplify into 3i square root of 7 all over 6. So now if I simplify this even more, I get negative 1/2 plus or minus square root of 7 over 2i. Those are my complex conjugate solutions. So one of them is negative 1/2 plus square root of 7 over 2i. The other one is negative 1/2 minus square root of 7 over 2i.